In the last video, we have completed all the previous year questions of analytical geometry, and today we are starting with the calculus. And in calculus, first topic which we'll be dealing with is limit continuity and differentiability. So let us solve questions related to limit continuity and differentiability. So the question 1 says that discuss the continuity of the function this. So we are supposed to check if the function is continuous or non-continuous. So if you see that this function fx is basically an exponential function, and the only problem it can have is only at x equals to 0. So we'll just check continuity of fx at x equals to 0. Otherwise this is a continuous function. Only x equals to 0 can be the point of discontinuity. So if a function is continuous, then it must satisfy this relation. So we'll just verify this relation for function fx and we'll see for ourselves if it satisfies or not. So first let's calculate left hand limit, that is basically limit x approaches 0 from negative direction of fx, which is same as writing limit as h approaches 0 f of 0 minus h. So the limit of this would be limit h approaches 0 1 upon 1 minus e raised minus 1 upon minus h. It is same as writing limit h approaches 0 1 upon 1 minus e raised 1 upon h. And when my h is approaching 0, 1 by h will approach infinity, and e raised infinity tends to infinity. So my this limit is equals to 1 upon 1 minus infinity. That is basically equals to 0. So my left hand limit is 0. Let's find out right hand limit. So right hand limit would be limit x approaching 0 from positive direction, that is basically limit h approaches 0 f of 0 plus h. So this is same as writing limit h approaches 0 1 upon 1 minus e raised minus 1 upon h. And as we have seen 1 by h approaches infinity as h approaches 0, then minus 1 upon h, this given limit can be written as limit h approaches 0 1 upon 1 minus 1 upon e raised 1 by h, and e raised 1 by h approaches infinity, then 1 upon e raised 1 by h will approach 0. So this limit is basically 1 upon 1 minus 0, that is equals to 1. But if you see that left hand limit is my 0 is not equals to 1, that is my right hand limit. So fx is discontinuous at x equals to 0. Discontinuous at x equals to 0. So this is a fairly simple question. We are just supposed to check the continuity of function, and you can always rely on this definition to check that. So let's move on to next question. So the next question says that find the value of p and q for which this limit exists and is equals to 1. So it is given that limit x approaches 0 x into 1 plus p cos x minus q sin x upon x cube. This limit is given to me as 1. So let's just solve this limit on left hand side and see for what value of p and q it is equals to 1. So if I just put value of 0 here in left hand side, I'll be getting 0 upon 0 form, that's indeterminate form. So we have to use L'Hopital rule and then move forward. So if I use L'Hopital rule here, then my limit on left hand side would be 1 plus p cos x plus x into minus p sin x minus q, derivative of sin x is cos x, divided by 3x square. Now if I substitute limit x equals to 0 herein, I'll be getting 1 plus cos 0 is 0 minus q upon 0. But this limit should be equals to 1 because that's what given to us in question. And this is possible only when we take 1 plus p minus q equals to 0 and then again apply L'Hopital rule. So from here I got my relation 1 as 1 plus p minus q equals to 0. So let us name this equation as equation 1. Now let's apply again L'Hopital rule on this term. Again using L'Hopital rule. So I'll be getting limit x approaches 0 minus p sin x minus p sin x minus px cos x plus q sin x divided by 3 to the 6x. Now if I substitute limit again x equals to 0 here, so I'll be getting a 0 upon 0 form again. So I have to use L'Hopital rule again. So again using L'Hopital rule, so I'll get a limit x approaches 0. It is minus 2p sin x derivative is cos x minus p cos x minus px sin x cos x derivative is minus sin x. So this negative will become positive plus q sin x derivative is cos x divided by 6. Now if I put limit here, so I'll be getting minus 2p minus p plus q divided by 6, and this must be equals to 1 because that's what given to us in question. So if I equate it, I'll be getting minus 3p plus q is equals to 6. Let's name it as 2. So I got basically two relations in p and q, and I can solve these two relations, linear relations in p and q, to get the value of p and q. So my p minus q is equals to minus 1 and minus 3p plus q is equals to 6. So if I solve it, I'll be getting minus 2p is equals to 5. So from here my p is minus 5 by 2. And if I solve for q, q is basically p plus 1. So my q is minus 5 by 2 plus 1. So from here I got my q as minus 3 by 2. So for p equals to minus 5 by 2 and q equals to minus 3 by 2, this limit is equals to 1. That's what we are supposed to find in this question. So let's move on to next question. So the next question says that they have defined delta x as a derivative of this, and where f is a real valued differentiable function. So f is a differentiable function, and alpha is constant, and they have given delta x as fx plus alpha, fx plus 2 alpha and fx plus 3 alpha upon f alpha, f2 alpha, f3 alpha, f dash alpha, f dash 2 alpha and f dash 3 alpha. So this is my delta x, and I am supposed to find limit as x approaches 0 delta x upon x. So if I directly put limit x equals to 0, so in denominator I be getting 0, and in numerator if I put delta x in this delta x, I'll be getting this term, determinant of f alpha, f2 alpha, f3 alpha, f alpha, f2 alpha, f3 alpha, f dash alpha, f dash 2 alpha and f dash 3 alpha determinant. But there is a property of determinant that says that if any of the two rows are equal or any of the two columns are equal, then determinant is equal to 0. So my delta 0 is basically 0. So I'll be, from here I got 0 upon 0 form. So here I have to use L'Hopital rule. So if I be using L'Hopital rule here, so my limit will become limit x approaches 0 delta dash x upon 1. So now I am supposed to find the value of delta dash 0 to get the required limit. So one way is to expand this delta x and then go ahead, and other way is to just directly find out the derivative and substitute x equals to 0. So let's say if let's say gx g1x, g2x and h1x. h2x is my, let's say, alpha x function. So derivative of this alpha x will be basically g1 dash x, g2 dash x, h1x, h2x plus g1x, g2x into h1, derivative of h1x and derivative of h2x. So we have to take derivative of a determinant, we have to take derivative row wise. Like first we have to take derivative of row 1, some derivative of row 2, some derivative of row 3. So like from using this result, if I found delta x, so that would be basically derivative of first row, that is f dash x plus alpha, f dash x plus 2 alpha, f dash x plus 3 alpha and f alpha, f2 alpha, f3 alpha, f dash alpha, f dash 2 alpha, f dash 3 alpha plus, now I'll be taking derivative of second row, but since it is given in question that alpha is constant, so derivative of f alpha will be 0, f2 alpha will be 0 and f3 alpha will be 0. Also we are able to take derivative because it is given in question that f is basically a real value differentiable function. Had they not given this condition, we won't be able to use this. So if I take derivative of second row, I'll be getting fx plus alpha, fx plus 2 alpha, fx plus 3 alpha, 0 0 0, f dash alpha, f dash 2 alpha, f dash 3 alpha plus derivative of third row. Again third row will also be constant, so derivative will be 0, so I'll be getting fx plus alpha, fx plus 2 alpha, fx plus 3 alpha, f alpha, f2 alpha, f3 alpha, 0 0 0. So we have another property of determinant that says that if any of the row or any of the column is completely 0, then the determinant is 0. So using that, this determinant will tend to 0. Likewise, this determinant will also tend to 0. So my delta dash x is basically reduced to f dash x plus alpha, f dash x plus 2 alpha, f dash x plus 3 alpha, f alpha, f2 alpha, f3 alpha, f dash alpha, f dash 2 alpha, f dash 3 alpha. But my limit is equals to derivative of delta x at x equals to 0. So if I put x equals to 0 here, so my delta dash 0 is f dash alpha, f dash 2 alpha, f dash 3 alpha, f alpha, f2 alpha, f3 alpha, f dash alpha, f dash 2 alpha, f dash 3 alpha. Now if you observe that my row 1 and row 3 become identical, so my this determinant will be basically equals to 0. So my required limit, that is limit x equals x approaching 0, delta x upon x is equals to 0. So this is the limit we are supposed to find in this question. So let's move on to next question. So the next question says that find dy by dx when fx comma y is this on using derivative on implicit function. So they have given fx comma y as log x square plus y square plus tan inverse y by x equals to 0. And if you observe that in question, they have specifically mentioned that we have to find dy by dx by taking derivative on implicit function. That means that we are not supposed to first find out value of y in terms of x and then solve it for dy by dx. We are supposed to use the find derivative dy by dx directly on this function. So if I take derivative of fx comma y with respect to x, so I'll be getting d by dx log x square plus y square plus tan inverse y by x equals to 0. So from here we'll be getting 1 upon x square plus y square, because derivative of log x is 1 by x, into 2x plus 2y into dy by dx, plus derivative of tan inverse x is basically 1 upon 1 plus x square, that is 1 upon 1 plus y by x square into d by dx of this term y by x. So we have basically used chain rule here. So if I solve this, I'll be getting 1 upon x square plus y square, 2x plus 2y dy by dx, plus x square upon x square plus y square into x dy by dx minus y into 1 by x square is equals to 0. This x square in denominator balances the 1 in numerator. So I can take 1 upon 1 plus x square y square common. So I am left with 2x plus 2y dy by dx plus x into dy by dx minus y equals to 0. So if I combine terms with dy by dx, I'll be getting 2y plus x into dy by dx is equals to y minus 2x. So from here I got my dy by dx as y minus 2x upon x plus 2y. So this is the derivative of y with respect to x, and that's what we are supposed to find in this question. So let's move on to next question. So the next question says that f is any function such that f of x plus y is equals to fx into fy for all x comma y belongs to real number. Also it says that f of 0 is not equals to 0 and f dash 0 is equals to 2. So it asked us that show that for all. So our claim is we're supposed to show that for all x belongs to real number, f dash x is equals to 2 times fx, and further we're supposed to find the function fx. So first let us show this and then we'll move ahead. So the given relation is f of x plus y is basically f of x into f of y. So if my x and y are both 0, then my f of 0 will be basically f of 0 whole square. So from here I'll be getting f of 0 either equals to 0 or f of 0 is equals to 1. But in the question it said that they have given us that f of 0 is not equals to 0. So I can eliminate this one. So from here I got my f of 0 as 1. So we'll be needing this relation in next steps. So we are supposed to show that f dash x is equals to 2 times fx. So my f dash x will be basically equals to limit h approaches 0 f of x plus h minus f of x upon h. I can write this using definition of derivative, but in question they have given us f of x plus y is basically fx into fy. So using that I'll be getting limit h approaches 0 fx into fh minus fx upon h, which is basically equals to, I can take fx as common, so it reduced to fx into fh minus 1 upon h. I can take out this fx outside limit because it doesn't involve term h, so it reduced to fx into limit h approaches 0 fh minus 1 upon h. Now if I put h equals to 0 in this term, I'll be getting 1 minus 1 upon 0, that is 0 upon 0 form. So I have to use L'Hopital rule to find out this limit. So that would be limit h approaches 0 f dash h upon 1. So this is equals to fx into f dash 0. And in question they have given me that f dash 0 is basically 2. So using that my f dash x is basically 2 times fx. So this is the relation which we are supposed to show And further in the question they have asked us to find the value of fx. So my f dash x is this, so I can write it as f dash x upon fx equals to 2. Now if I integrate, so I'll be getting integration of f dash x upon fx equals to integration of 2 dx. So this will be basically log of fxx equals to 2x plus c. But I know limit of f, value of f in x equals to 0, that is 1. So using that, log of 1 will be equals to c, but log 1 is 0. So from here I got my c as 0. So my function fx is basically e raised to x. So this is the function fx which satisfies the given relation above. So let's move on to next question. So the next question says that f is a function from closed interval 0 comma pi by 2 to r, and it is a continuous function, and f is continuous, and function fx is defined as cos square x upon 4x square minus pi square for 0 less than equals to x less than pi by 2. And we are supposed to find out the value of f pi by 2. So in the question they have given us that f is a continuous function. So limit x approaches 0, x approaches pi by 2, fx will be basically equals to f of pi by 2. So we can find out value of f of pi by 2 if we can calculate value of this limit. So let's just find out value of this limit. That would be limit x approaches pi by 2 fx, that is equals to limit x approaches pi by 2, and my fx is cos square x upon 4x square minus pi square. This would be equals to limit x approaches pi by 2 cos x, and derivative of cos x will be minus sin x divided by 8x, and this term is equals to limit x approaches pi by 2 into 1 by 4 cos x into sin x upon x, it's minus 1 by 4. Or maybe I can write it as this. So this term can be written as minus of sine 2x upon 8x. Now if I put value x equals to pi by 2, so I'll be getting minus sine pi upon 8 into pi by 2. But my sine pi is equals to 0, so my limit is 0. So f of pi by 2 is basically equals to 0. And that's all we're supposed to find in this question. So let's move on to next question. So the next question says that fx is a function defined as this, and we're supposed to check if function fx is differentiable at x equals to pi by 2, and if it is differentiable then we're supposed to find its derivative at x equals to pi by 2, and if it is not differentiable then we're supposed to give the proof of it. So let's see function fx. So my fx is mod cos x plus mod sin x. So we are supposed to check its differentiability at x equals to pi by 2. So this function would be defined as cos x plus sin x for all x less than equals to pi by 2, and minus cos x plus sin x for all x greater than pi by 2 but less than pi. So we are supposed to check its differentiability at x equals to pi by 2. So first let us see that if it is a continuous function or not. So you can also see that directly, because sin x and cos x are both being trigonometric functions are continuous functions. So my fx is also a continuous function. Now I am supposed to check its differentiability at x equals to pi by 2. So let's find out its left hand derivative. So that would be equals to limit x approaches pi by 2 negative f of x minus f of pi by 2 upon x minus pi by 2. So that would be basically equals to limit x approaching pi by 2 sin x plus cos x minus f of pi by 2 would be 1 divided by x minus pi by 2. So this limit would be equals to, if I put x equals to pi by 2, I'll be getting a 0 upon 0 form. So I have to use L'Hopital rule here. So using L'Hopital rule, I'll be getting limit x equals approaching pi by 2. Sin x derivative is cos x and cos x is minus sin x upon 1. So if I take limit, so this limit will be equals to minus 1. Now let's find out right hand derivative. That would be basically equals to limit x approaches pi by 2 positive from positive direction fx minus f pi by 2 upon x minus pi by 2. So this thing is basically equals to limit x approaching pi by 2 minus cos x plus sin x minus 1 upon x minus pi by 2. Now if I again substitute value of x equals to pi by 2 here, so I'll be getting 0 upon 0 form again, so which is an indeterminate form. So we have to use L'Hopital rule again here. So using L'Hopital rule, I'll be getting derivative of cos x is minus sin x plus cos x upon 1. So if I take limit, so my limit will be equals to 1. So if you see that my left hand derivative is not equals to right hand derivative. So from here, so fx is not differentiable at x equals to pi by 2. So this is what we are supposed to show. So let's move on to next question. So the next question says that show that a function fx defined on open interval a comma b of R, if the function is convex, then f is continuous. Also by example, if the condition of open interval is dropped, then the convex function need not be continuous. So they have given us a function f defined on a comma b, that is open interval of R to R. It is a function and fx is basically a convex function. So we are supposed to prove that any such function defined on open interval a comma b is continuous. So we are supposed to prove that fx is a continuous function. So since it is given that fx is a convex function in interval a comma b, then f must be satisfying x into lambda plus 1 minus lambda into y. This term must be less than equals to lambda into fx plus 1 minus lambda into fy for all x comma y belongs to open interval a comma b. And here my lambda is in between open interval 0 comma 1. So this is the relation we got because fx is given to us as a convex function, and this is the relation a convex function satisfies. So a comma b is an open interval and set of real numbers is a dense set. So from there we'll be getting c comma d belonging to open interval a comma b such that a is less than c, is less than x, less than d, which is less than b. Now for any number x, I can write x as d minus c divided by d minus c into x. So I can write it as dx upon d minus c minus cx upon d minus c plus cd minus cd. this term is basically equals to I can take d common from this one and this one, so I'll be left with d into x minus c upon c minus d plus c into wait, I think I have done something incorrect. So yeah, I think I have done something incorrect. So I'm supposed to add this divided by d minus c. So if I simplify it, this term will be basically equals to d into x minus c plus c into d minus x divided by d minus c. So my x can be written as d minus x divided by d minus c into c plus x minus c divided by d minus c into d. So I can write any x belonging to a comma b like this. Now using this convexity result, let's name it as star 1. So using star 1, my f of x will be basically less than equals to d minus x upon d minus c into f of c plus x minus c upon d minus c into f of d. So what I can do is I can combine terms with x. So if I do so, I'll be getting x into f of d minus f of c upon d minus c plus d into fc minus c into fd upon d minus c. Now my fx is less than equals to basically this term, and I can simplify it further. I can add and subtract f of c. So if I do so, I'll be getting x into f of d minus f of c upon d minus c plus f of c minus f of c plus d into f of c minus c into f of d upon d minus c. So this relation can be written as equals to fc plus this term x into fd minus fc upon d minus c, plus if I take LCM of these last two terms of the previous equation, so I'll be getting dfc minus cfd minus dfc plus cfc divided by d minus c. So this term balances this one. So we get it as fc plus x into fd minus fc divided by d minus c. Minus c we can take common, so we'll get fd minus fc divided by d minus c. So this term is basically equals to fc plus fd minus fc divided by d minus c into x minus c. So I got the relation for fx. Now my a comma b, so let's assume that this is a, this point is b. Then since R is a dense set, so there must be exist in any point S and T, comma U, comma V in between the set R. Using density result, S, comma T will exist, and again using that result, U and V will exist. So if I use this above result on this interval S comma U comma V, so I'll be getting my f of U less than equals to f of s plus f of v minus f of s divided by v minus s into u minus s. So this, if I simplify this relation for f of v, so I'll be getting, so this will basically reduce to f of u minus f of s upon u minus s into v minus s plus f of s, and this will be less than equals to f of v. So I have just taken this term on left hand side and then divided by u minus s and multiplied by v minus s, and then added f of s on both sides, so I got this relation. Likewise, if I use this above result on this interval u comma uv u comma t, open interval u comma t, so I'll be getting f of v is less than equals to f of u plus f of t minus f of u upon t minus u into v minus u. So I got a relation. So my f of v, using this, let's name it as star 2, and this let's name it as star 3. So using star 2 and star 3, my f of v is basically less than equals to f of u plus ft minus fu upon t minus u into v minus u greater than equals to f of u minus f of s upon u minus s into v minus s plus f of s. So I got an inequality in f of v u. So if I take limit v approaches u, so this will be basically less than equals to limit v approaches u f of v less than equals to, when v approaches u, this term will become 0, so this whole term will reduce to 0, so I'll left with f of u. And likewise, when v approaches u here, so I'll get f of u minus f of s upon u minus s into u minus s plus f of s. This term balances out this one, so on left hand side also we will get f of u. So I got relation as f of u less than equals to limit v approaches u, fv is less than equals to f of u. And using sandwich theorem, we'll get limit v approaches u, f of v is equals to f of u. So we have proved that the function fx is continuous because this is the result of continuity, and we have proved it for open interval s comma t. Likewise, we can extend it to open interval a comma b. So any such function f defined on open interval a comma b, which is subset of R to R and is convex, so any such function is continuous. Now let's see example that if we drop the condition of open interval, does that function is not continuous. We are supposed to give one such example. So let's see any such example. So let us assume that fx is a function that is equals to 0 in when x belongs to open interval 0 comma 1 and is equals to 1 at x equals to 0 comma x equals to 1. So fx is a function defined on closed interval 0 comma 1, and you can easily observe that this function fx is not continuous at its endpoint. Now if we can show that this function is convex function in closed interval 0 comma 1, then we are done. So let's do that. So if you observe that in open interval 0 comma 1, fx is taking value 0, so the graph of if we take any point in between 0 comma 1 and form a line joining those points, that is, let's say x1 comma fx1 and x2 comma fx2, then any such line will be basically above this graph of x-axis. That will be basically lying on x-axis only. That line would be lying on x-axis only. Likewise, we can check for endpoints as well. Like first we can take 0 comma f0 and any other point, let's say x1 comma fx1, and check for these two, check for convexity of fx in this interval. Likewise we can take x2 comma fx2 and comma 1 comma f of 1, that is 1 again. So we can check convexity in this subinterval as well, and this function is basically convex but not continuous in closed interval 0 comma 1. So the above relation holds only for open interval a comma b and not for a closed interval. So let's move on to next question. So the next question says that suppose R be set of all real numbers and f is a function from R to R such that, so f is a function from R to R and f satisfies two condition, f of x plus y is equals to f of x plus f of y, and second condition is basically f of xy is equals to f of x into f of y, and these results holds for all value of x and y in real. So we are supposed to show that for all x belonging to R, either f of x is 0 or f of x is equals to x. So our claim is for all x in real number, so either f of x is equals to 0 or f of x is equals to x. So let us assume that f of x is not equals to 0. So if f of x is not equals to 0, so we are supposed to show that f of x must be equals to x. So in the question they have given us as f of x plus y is equals to fx plus fy. So if my x is equals to y, so from here I will be getting f of 2x is equals to f of x plus f of x, that is f of 2x is basically equals to 2 times f of x. Now they have also given us as f of xy is equals to f of x into f of y. So if I take my y is equals to 2, so f of 2x will be basically equals to f of x into f of 2. So from star 1 and star 2 we can basically compare value of f of 2x. So we will be getting 2 times f of x equals to f of 2 into f of x. So from here we'll be getting f of x into 2 minus f of 2 is equals to 0. But we have assumed that f of x is not equals to 0. So from here we'll be getting f of 2 is equals to 2. Now we can generalize this result. So let we can generalize this result. So f of x plus x k times will be basically equals to k times f of x, that we got using we can write it as f of x plus k minus 1 times x, that is equals to fx plus f of k minus 1 into x, and this is basically equals to f of x plus f of k minus 1 into f of x. And from here I can take f of x as common, which is basically equals to 1 plus f of k minus 1, and this term is basically f of kx, which is also equals to f of x into f of k is equals to f of x. Yeah, we can, no, I guess I have done something incorrect. We can generalize it by taking, like we have done from x equals to y, so we can take y is equals to 2 times x, and then we'll be getting f of 3x is equals to 3 times fx, and then we can use induction to get f of kx equals to k times f of x. Likewise my f of xy is basically equals to f of x into f of y, So I can take my y as k. So from here I'll be getting f of kx equals to f of x into f of k. Now if I compare star 3 and star 4, so I'll be getting k times fx equals to fk into fx. But I have assumed that my fx is not equals to 0. So from here I'll be getting f of k is equals to k. And we have assumed k to be any real number. So we got f of x is equals to x for all x belongs to R. Likewise, now to do the contradictory part, we can assume that f of x is not equals to x, and we can show that fx is 0. Like here, if in this equation, if I assume that fx is equals to x, if x is not equals to x, then my fx will be 0, and I can generalize this part for f of x plus xk times as well. So we'll be getting either f of x is equals to 0 or f of x is equals to x for all x belongs to real number. So let's move on to next question. So the next question says that f is any function such that so f is any function such that defined from closed interval 0, 1 to closed interval 0, 1, and it is given that f is a continuous function on 0, 1. So we are supposed to show that there exists a point C. So our claim is basically there exists a point C belonging to closed interval 0, 1 such that f of c is equals to c. First, let us observe that f is a function with domain 0, 1 and range also 0, 1. So for all x belonging to 0, 1, I'll be getting fx in between 1 and 0. So let's name this relation as 1. Now let us define a function gx as f of x minus x. So from here I'll be getting g of 0 as f of 0 minus 0, that is equals to f of 0, and g of 1 as f of 1 minus 1. Now from relation 1 we will get f of x is greater than 0 for all x belonging to 0, 1. So from here my f of 0 will be greater than equals to 0. So using that I'll be getting g of 0 is greater than equals to 0, and from this relation only f of x is less than equals to 1. So f of x minus 1 is less than equals to 0 for all x belonging to 0, 1. So if I take my x as 0, so f of 0 minus 1 is less than 0, less than equals to 0. So from here I got my g of 1 is less than equals to 0. Now if this equality holds, that is if g of 0 is 0, then I'll be getting f of 0 equals to 0. So I got a c, that is c is equals to 0, which belongs to closed interval 0, 1, for which my f of c is equals to c. And likewise, if this equality in this relation hold, so I'll be getting my g of 1 is equals to 0. So from here I'll get f of 1 minus 1 equals to 0. That gives me f of 1 is equals to 1. So again I got a c, that is equals to 1, which belongs to closed interval 0, 1, for which my f of c is equals to c. Now let us assume that if equality holds, then I got a point c in between closed interval 0, 1, for which equality f of c is equals to c. Now let us assume that g of 0 is strictly greater than 0 and g of 1 is strictly less than 0. So I got this, and also it is given that fx is a continuous function. Fx is a continuous function in closed interval 0, 1. So So if fx is continuous in 0 comma 1, then gx that I defined as fx minus x, then it is also a continuous function because it is basically addition of two continuous functions, that is fx and minus of x. So my gx is also a continuous function, and so gx is continuous, and my g of 0 is greater than 0 and my g of 1 is less than 0. So since it is a continuous function, so there exists c belongs to open interval 0 comma 1 such that g of c is equals to 0. So from here I'll be getting f of c minus c is equals to 0. So which gives me f of c is equals to c for some c belongs to 0 comma 1. So the given relation holds. I got this using a mean value theorem result. So the given relation holds that for if this is a continuous function in between 0 comma 1 closed interval, then there exists a point c in closed interval 0 comma 1 such that f of c is equals to c. So let's move on to next question. So the next question says that find the supremum and infimum of function this on interval 0 comma 1. So fx is basically x upon sin x on 0 comma pi by 2. So if I take derivative of fx, I'll be getting sin x minus x cos x divided by sin square x, and here x is basically belonging to 0 comma pi by 2. Now this denominator term is basically sin square x will always be greater than equals to 0. It cannot be 0 because 0 is x is not taking value 0, x is just approaching 0. Now if I can show that this numerator term is always greater than 0, so I'll be getting fx as increasing function, and then using that result I can easily find out supremum and infimum of this function fx. So let us assume that gx is equals to sin x minus x cos x. So I'll show that gx is always greater than 0, and we can just find out value of this infimum and supremum. So if I take derivative of gx, I'll be getting cos x minus minus x into minus sin x, that is basically equals to x sin x. And since x is taking value from open interval 0 to closed pi by 2, so my g dash x will always be greater than equals to 0. So my g dash x is increasing function, so my g of x will always be greater than g of 0, and my g of 0 is 0. So my g of x is always strictly greater than 0. So from here I got my f dash x as greater than 0. So if my f dash x is greater than 0, then my fx is increasing function on 0 comma pi by 2. So my infimum will be when x approaches 0. So fx when x approaches 0 is basically limit x approaches 0 x upon sin x, and this is equals to 1. And my supremum will be when x is approaching pi by 2. So limit x approaches pi by 2, fx will be limit x approaching pi by 2 x upon sin x. So this is basically equals to pi by 2. So my infimum is 1 and my supremum is pi by 2. So let's move on to next question. So the next question says that a function fx is defined from r to r, and it is defined as x when x is rational and 1 minus x when x is irrational. So we are supposed to show that f is continuous at x equals to 1 by 2 but discontinuous at all other points in R. So this is a famous Dirichlet function, and it's usually asked, like this question is repeated many times. So let's see how we can show that. So fx is given to me as x when x is belonging to rationals, and 1 minus x when x is belonging to irrational. So we are supposed to show that fx is continuous at x equals to 1 by 2. So let us assume that x greater than 0 and delta is greater than 0 such that x minus 1 by 2 is less than delta. Then my fx minus f of 1 by 2 will be basically equals to x minus 1 by 2 when x is belonging to rationals, and 1 minus x minus 1 by 2 when x is belonging to irrational. This is basically equals to 1x minus 1 by 2 for all x belonging to R, because from here I'll be getting x minus 1 by 2 only. So my fx minus f of 1 by 2 is basically is equals to modulus of x minus 1 by 2, and this is less than epsilon for epsilon is equals to 0. So using definition of continuity for epsilon is equals to delta, which is greater than 0, mod of fx minus f of 1 by 2 is less than epsilon whenever my x minus 1 by 2 is less than delta. So using this, my fx is basically continuous at x equals to 1 by 2. Now I'm supposed to show that this function fx is discontinuous at all other points. So let us assume that a not equals to 1 by 2 be any rational number. Then since a is rational, so f of a will be basically equals to a. So also we know that set of real numbers is a dense set. So there lies like infinitely many numbers in between any two rationals and irrational. So for every positive n, we can find an irrational number an such that my an is approaching to a, that is an minus a is less than 1 minus n, and I can find any an for any such value of n. Now using sequential, if I use sequential criteria of continuity, my an is approaching to a, then my f of an must approach f of a by sequential criteria. Sequential criteria of continuity. So but my an is irrational number, so limit n approaches infinity, f of an will be basically minus 1 minus an, because my an is irrational but my f of a is a, and this is not equals, if I take limit here n approaches infinity, then this will be 1 minus a, which is not equals to a, because I have assumed that a is not equals to 1 by 2. So this contradicts our assumption that f is a continuous function. So likewise we can assume that a to be any irrational number, a be any irrational number. So if a is irrational, then f of a will be basically 1 minus a, and we can, because of the dense condition of the set of real numbers, so for every positive n we can find an rational an such that it approaches a, that is an minus a is less than 1 by n. Then using sequential criteria of continuity, since an approaches a and we are assuming that f is continuous, then f of an must approach f of a. But since an is rational, so f of an will approach an, limit n approaches infinity, but f of a is 1 minus a, and these two terms are equal if and only if a is 1 by 2, but we have assumed that our a is not 1 by 2. So again from here we got a discontinuity of f when x is not 1 by 2. So f is discontinuous for all x not equals to 1 by 2. So let's move on to next question. So the next question says that for the function f, so f is a function from 0 comma infinity to r, and fx is defined as x square sine 1 by x, 0 less than x less than infinity. We are supposed to show that there exists a differential function g that extends f. So we are supposed to show that there exists a function from r to r, which is basically extension of a function fx. So if you observe that sin x is basically a continuous function in between 0 comma x comma infinity, and 1 by x is also continuous in upper interval 0 comma infinity, and then using composition of continuous function is continuous, so sine of 1 by x is continuous. So if my sine of 1 by x is continuous and x square is also continuous, being a polynomial function, so my fx is basically continuous function. Now I need to check differentiability of fx at this endpoint x equals to 0. So limit x approaches 0 positive, fx minus f0 upon x will be basically limit x approaches 0, fx, that is x square sine 1 by x minus f of 0 is 0 upon x. This is basically equals to limit x approaches 0, x into sine 1 by x, and this differentiability limit will be basically equals to 0. So my fx is basically differentiable at x equals to 0. So I can define my function gx as fx for x belonging to open interval 0 comma infinity and 0 for x belonging to minus infinity 0. So since my fx is also taking value left and right hand derivative as 0, and my left hand derivative of 0, gx will also be 0, so gx is basically a differential function which is basically extension of fx. So my gx is basically x square sine 1 by x, 0 less than x less than infinity and 0 for minus infinity to x minus infinity to 0. So this is basically extension of function f. So we'll discuss other questions of this topic in next video, because otherwise video will be too long to upload. So thank you for watching this video.